Hello, everyone. I'm going to be talking a little bit about TensorFlow today. This is an open source machine learning library that we made open source about a couple of months ago now. So I'm from the Google Brain team, and we are part of research at Google. We use this every day at Google, and once we started building it a couple of years ago, we decided it's probably interesting to the rest of the world as well, and let's see if open sourcing will actually help everyone as well. So first, the outline of the talk. So the first part, why do we care? I probably don't need to tell you guys why machine learning is interesting. I'm sure most of the people here are familiar with data science and are interested in that. But I'm just going to walk through a few examples and things that are interesting and why we really work on this. Then I'm going to talk a little bit about what TensorFlow is, how do we use it, what do we do with it, and then deep dive a little bit into under the covers, what's it based on, what the ideas there are, and then give you some examples of how you might write real TensorFlow programs and do machine learning in TensorFlow. And at the end, I'll give you some resources for you to continue your learning and look online for more things as well. So first, why do we care? Machine learning has been given some great results recently. Over the last few years, we've seen great improvements in some of these areas, especially image classification. You give an image, and once you train a model with lots and lots of images and labels, you can train it to actually give it an image that it's never seen before and predict what it is. In this example, a lion, of course. Another area that's worked really, really well is speech-to-text. If you've ever tried voice search on your phones, that's machine learning at work. It basically takes your voice input, converts it to text, and allows you to do searches with that. Again, something that wasn't really practical just a few years ago, and in the last couple of years, it's become a reality, and a lot of people use it now. At least I use it almost every day. Another one is search itself, the bread and butter for Google. Something we apply machine learning to, and one of the things that's important there is users give a query. There are millions of, well, actually trillions of documents now. The first part is, of course, whatever documents match, but even then you're left with millions and sometimes even billions of documents. How do you rank them? How do you decide which ones to show? The first page is only going to show 10 results. So figuring out what is the most likely thing for this user, that's something that we use machine learning for. Another example is translation. Some of you might have tried Google Translate, where you might type in a text or give it a text in English and get out the output in French or many other languages. We support like 100 or so languages, I believe. That's another one that machine learning is being used for. And the last one, which is a little bit more of a research topic, but it's showing some good results now, is image captioning. Give it an image, and it tries to describe an image. The text that you see here in this case is actually generated by a machine learning model. So these things are getting really, really good. Of course, they make mistakes as well. They're not perfect there. But some of the other areas of, like, for example, the image recognition stuff has really gone from being 40, 50% errors to nearly no errors or nearly human accuracy, I guess, especially in certain areas. So all of these examples that I was talking about, they're actually, they came from something called deep learning, which is this branch of machine learning, which has been giving a lot of good results over the last few years. In fact, that's what our focus has been in our team, to take deep learning and scale it up and apply it to tons and tons of problems and see how we can make progress. And it's used across Google in lots of places. So the graph here sort of shows you how it's picked up over the last few years. Of course, machine learning has been around for a long time, and Google's been using that. This particular graph is specifically for deep learning. And that I show this partly because that's what motivated the writing of TensorFlow and the previous version of TensorFlow called Disbelief at Google, and eventually us open sourcing it. So as you see, many products, ads, Android, and a bunch of others written here. So just to give you some real-world examples of things that you're probably using today, if you use Google Photos, you probably see it automatically labeling a bunch of things. You can search for things in there. You can search for people, of course, but you can also search for, say, the beach or a car, and it'll show you pictures that are relevant to that automatically. Something that you used to do yourself, where you have to tag every picture with the right people, the right faces, et cetera, you don't have to do much anymore. And it's getting better every day. Another example is Translate that I just mentioned. There's actually an application that you can stake, and you just point your phone at, say, a sign in a different language, and it'll convert it for you right there into the language that you care about. Another one is Google Keyboard. As you type, it predicts what you're going to type or suggests the right correction, et cetera. Again, something that uses machine learning. So the basic idea is, of course, I'm showing you a few examples of places where machine learning is used. But just to drive home the point, it's actually used in many, many different products every day. So a lot of these are products probably that you use in different ways. And these are just Google products. You probably use many, many more that use machine learning. So it's really widely used. People say, machine learning is the future. I really think it's not really the future. It's here already. Yes, it's always going to get better. There's still tons to do, but it's here to stay. It's already being used in everything that you do. So from there, let's go talk about TensorFlow, as the main topic of this talk today. So as I was saying, we started with deep learning a few years ago, about 5 years ago, I think. And we started seeing that, OK, at that time, deep learning wasn't as popular as it is today. It wasn't a household name or whatever, at least not that common in the machine learning community as well. Even the neural networks, which this is also known as, they are like from the 1940s or 50s, and they've changed and improved over time. It's only in the last 4 or 5 years that we're starting to see results. In our team, when it was formed about 5 years ago, there were very, very early results in some areas, and it seemed like if we scale it and give it more data, it's going to do well, but we didn't know. So we decided to try it out. At that time, we built a system called Disbelief. We scaled it up to use thousands of computers, and we published a paper on that. We started using it, and we saw great results in different areas. We started using it for speech and a few other products, as you saw in those charts. And then over the last few years, as we saw things scale up, things change, a year and a half or so ago, we decided it's probably time to rewrite the system because from the point where we started to where we are now, things have changed a lot. It makes sense for us to continue to scale further and try something out. That's when we decided to really open source this. In fact, Jeff Dean, who's the lead for our overall team, it was his idea, let's take this and why not just use it here? Why not make it available to everyone outside as well? So now, what's TensorFlow? Of course, I've mentioned it is a machine learning library that's been open sourced. It's being used by hundreds of products. That pretty much the same code that you would use outside that's open source. That same code is run internally on many, many Google servers. It's used by a lot of people there. It's used by data scientists, by researchers, and developers, right? We aim to help everyone. It's not just for doing research. And we also want to enable the building of the next generation, the smart applications, some of which you see. Every little thing that you do, there are applications today that are great on the mobile phone, et cetera. We think they can be better. And whatever kind of thing you do, right? If you can learn from what users really want, you can do a much better job of providing them the right application as well. So going a little deeper on who it's for, these are the 3 sort of pillars that I think of. They are the researchers or the machine learning scientists who can use this to really drive their research, build new kinds of models, completely new ideas, right? Publish papers, and then also share code. We definitely wanted to make it open source so it's easier for people to share real code with other researchers and speed up the whole process of collaboration and building on top of others' work. The next part there, which is sort of related, is data scientists who may not necessarily want to build new algorithms, but they want to take these algorithms and apply them in very interesting ways to data sets that they might have. And this enables them by making this whole library of algorithms available as well as part of that package. And this library is growing very, very rapidly. We've, of course, seeded it with a bunch of algorithms ourselves, but we see a lot more people starting to add more as well. And we plan to push more and more out as we publish new papers. Our focus is going to be try and get as many new algorithms in there as well for people to use. And then going from there, the next step in a lot of companies is, OK, great, this algorithm seems to work well on my data, but how do I actually use it? How do I use it in production? I mean, a lot of times the systems for training and production deployment are very, very different. What we aim to do with this is to really be able to use the exact same APIs that you use for your training and deploy that in production as well. whether it's on your data center thing or on your smartphone or wherever, you should be able to really use the same API, the same software for doing that. So it makes the whole process much more easier. So now let's get a little bit into the architecture of TensorFlow, right? In the middle, there's the core execution engine that's all written in C++ for performance. That's something we care about, of course, when we run it on so many different machines. And then on top, for the end users, there are these different front ends. The most common one we use today is the Python front end that the users use to specify their models, to do their training, et cetera. Then there's a C++ front end that a lot of users use for production. You can use it for training, of course. It provides the same kind of functionality. And the way we've layered it, that it's easy to add more front ends. And in fact, we're trying to push more and more of the functionality from the Python one into the C++ one, so you can very easily add bindings to different languages. There's been interest for JavaScript, Java, all kinds of other languages as well. It should be fairly easy to add some of them. Now, this core execution engine, that's the front end. Now, the back end being, where do you run this stuff, right? And of course, we support CPUs running on your workstations, data centers, laptops, whatever. We also support GPUs, which are very widely used for deep learning today. And you don't have to be limited to just one GPU. You can use many on a machine. In the future, you'll be able to use it on running many, many machines in a distributed fashion as well. That's, of course, the data center side of things. We also support running the same thing on a mobile phone. In fact, some models run already, in our case, on the mobile phones today. You can run on Android already. iOS support is in progress. It's nearly there. So you'll be able to run it pretty much on any phone. And then in the future, we see a lot more embedded devices and custom ASICs that people are building today for neural nets and deep learning stuff. And we definitely see support for that coming up as well. We've been talking to different vendors, and there's interest in supporting them through the same TensorFlow API. So you don't have to worry about it. So that's sort of the high level there, right? What it looks like at a high level. Let's dive a little bit deeper into how the internals work, how it's designed, et cetera, just to give you some more idea of how it works. So a few things about the architecture first again. Traditionally, there are many machine learning systems, right? Machine learning is a fairly old field, and there are different kinds of libraries that you'll see. There are like probably hundreds of libraries out there. Typically, you would see each library supporting a few models, a few model types. There are some that are more general. But they would still be very focused on very specific data types, very specific things, and they would be built around specific algorithms. So the way we decided to build TensorFlow was to start with very flexible structures and the kind of optimization we do with it. So it's built on what I call data flow paradigm based on directed acyclic graphs. And so anything you can express in the form of those graphs, you can really run with TensorFlow. It's, you typically define the graph in some high-level language. It gets compiled and optimized to really give you the same kind of optimization that you would running in C++ itself. And then it can be run on whatever devices you have. So like I mentioned, it's the computation is like a data flow graph. So for those of you not familiar with data flow, the idea is in a typical architecture when you're, say, programming with C++, things are executed sort of one thread at a time, right? The way you write things, it's going to be executed by, say, one core or whatever, unless you explicitly do threading. In this case, with data flow, what happens is each node in the graph is sort of like independent of each other, right? Unless there's a very specific dependency or an edge between those, right, a directed edge. So if there are two nodes that don't have a direct dependency, then you can actually schedule them completely independently. So the parallelism itself is built in the graph, and that allows you to optimize these things much better. That's part of the reason why we decided to go this way. So here's a very simple example. That's a graph of nodes. It's basically doing a very simple softmax where you have biases and weights going into, you do a matrix multiply with biases and weights, add the biases, weights and inputs, add the biases, apply a softmax, and then you have some targets based on which you apply cross entropy loss for your training. So typically, of course, it's a much bigger graph, but it's a very simplistic example. And then the edges that you see here are basically the data flowing through. And these are what we call tensors. They're really n-dimensional arrays. And in our case, the n-dimensional, the n can be more than 2. 2 would be a matrix, 1 would be a vector. You can have those, of course, but say you have an image, which is a 2D matrix, but then if you have a color image that's, say, RGB in that, so that's a third dimension. Now put a batch of them together, typically train mini batches or whatever, so that's a fourth dimension. So very easily you get to 4 dimensions and stuff.
When you say edges are n-dimensional, do you mean that the tokens that flow along the edges are n-dimensional?
That's right. So the tokens that flow along the edges, that's what we call tensors, and those are n-dimensional arrays, really, right? Not the generalized physics tensors in some sense. So typically in deep learning, what you do is you have a sort of a forward pass where you're doing inference and computing a value or a prediction, and then you use backpropagation through a backward pass to compute the gradients and then apply them. In this case, the backward pass is also part of the graph. It's also added typically automatically to the graph based on auto differentiation. And in this particular example, you might have a bunch of operations here that compute the gradients with respect to the bias. Then you multiply it with some learning rate, and if you're doing stochastic gradient descent, then you just update the biases. So all of this is part of that one graph for training, and it's fairly easy to build out. And I'll show you some examples later on in the talk. Now you could take the same graph and you can distribute it across many different devices. Those could be different threads, different processes, different GPUs, or different machines. Excuse me. And it's very easy to do. You can just say, OK, if I want to choose manually, then I could say, this part of the graph is going to be on this particular GPU. This part is going to be on another GPU, and just let it run. Of course, if you want to distribute things further, there are simpler ways of doing that where it automatically picks large parts of the graph and puts them on the devices for you. And in this case, now, once you have things on different devices or different threads, right, many of them can run in parallel. As long as there are no direct edges between them, then they can be scheduled in parallel, and they can really utilize the power of these different devices and machines together. So as I was mentioning, it's a data flow graph. Of course, the examples that I showed you were very, very small. In practice, it's typically hundreds to thousands of nodes and edges. In fact, some of our image models are, say, tens of thousands of nodes as well. So they can be pretty big, and TensorFlow handles that pretty easily. We've run things with hundreds of thousands of nodes as well. In this case, inference is just, you might have a graph that has both inference and training in there, but inference might be you can just run part of the graph and just get the predictions in there. So this particular image that I show you, it's actually on the website as well. There's some visualization tools as well that you can use to get things like this. So now let's go a little bit, that's sort of how the basic ideas behind TensorFlow and how it's built.
Question about the previous slide. So there's thousands of nodes. Are they all, or tens of thousands of nodes, are they all like hand-coded?
So the question was, if you have tens of thousands of nodes, are they all hand-coded? And it depends. You can, of course, right? But we do have higher level libraries which sort of combine things. So for example, if in case of neural nets, you want to do a fully connected layer, we have a function which says, OK, I want a fully connected layer with so many outputs, and it'll add maybe the 3, 4, 5 nodes that are needed for that. And so you typically build on these libraries. There are some that are already available, and we continue to add more. But when we build these large graphs, they're definitely composed of these lower level functions sort of that you generate. One more thing actually we're working on, and we have some experimental support actually on that point, was we have the notion of functions coming in which would allow you to reuse parts of the graph in many, many places without duplicating them. Today, when you use functions in Python, it actually duplicates the same. It's sort of inlined in the graph. So let's go a little bit into writing real programs. What does it look like? What's the language look like? And all my examples are going to be using Python, since that's really the most well supported. It's a pretty common language for data scientists today. So here's the skeleton of the first program that you might write, a hello world, of course, right? So you import TensorFlow, create a session. A session is really an instantiation of a graph, or really what your execution environment really. So first thing you do is define some operations, in this case just a constant, hello world. as this example shows you, we do support strings as well. As other types, I'll go into some other examples of types we support. And then you just say session.run C, and you print it. What the session run C basically does is it executes that constant, takes its output and return it, and then of course the print function in Python just prints that out. So you'll see a hello world printed in this case. Here's a slightly more bigger example, right? We just want to do a matrix multiply and then add some biases, which is a typical linear neural net layer, I guess, or a linear layer, I guess. In this case, we've started with just the inputs being constant, examples, weights, and biases. You define them. You define outputs as a matrix multiply of those two, and then you add the biases, just as you might do with another library, say NumPy, or some just in Python itself as well. So the first 4 lines that you see here aren't really doing any execution yet. They're really building the graph at that point. And then when we actually say session.run outputs, that's the point when it actually does the execution and then gives you the output, right? Returns the output in this case of the value of the outputs itself. So here are some of the types we support, and there are more being added. There's more work being done to support smaller types like 8-bit integers and maybe 16-bit floats as well. Stuff that people are using nowadays to speed up things, especially on inference, but sometimes in training as well. So here's how you might define different kinds of constants. You can specify the shapes. You can just have a float vector. You can do an int32 vector. You can specify the shape afterwards. You can specify the shape by defining it within the Python constant itself. You can do it in all kinds of ways there, really. You can also use NumPy values, which a lot of Python folks use, and combine it and use it nicely with TensorFlow. So you can pass in NumPy arrays. So for example, you might use NumPy random thing in this case. Of course, we do support a lot of these functions that NumPy supports, for example, random generation, et cetera. So it's probably more efficient to use the TensorFlow ones in this case, but if you really wanted to, you could. Here's how you might build different kinds of expressions. You have a constant, you're doing 2 matrix multiplies and then adding them together. To give you an example, so in this particular case, at this point, like I was saying, it's not really running anything. It's just building the graph, and the graph that you see at the top right corner there, that's the one that it's built in this case. So you have the constant x. There's a matrix multiply which takes in x in both sides, and then another one which multiplies it with a different constant, and then you add this together. So this part is just building this graph and nothing else. Now when we actually ask it to run something, that's when it actually executes the graph, right, and returns the value of that plus there. The c.eval is really just a shorthand for running the graph up to that point and returning that particular value. There's the notion of variables. So you can hold state. For example, with machine learning, you want to hold parameters. So you would use variables for that. But it doesn't have to be just that. For example, typically in machine learning, you're iterating through many, many, many steps. And we hold a step number in just a variable in there, which is, say, an int64. So you could really use those variables to hold any kind of value in there. In this case, we want to hold, initialize it to this particular value. Note, however, what you see in the top there, the variable is not really initialized at this point. That's what we want to initialize it, and that's what we specify. It's not done yet because that's a separate initialization step as well that you need to remember to do. So the first thing you typically do is you initialize all the variables and you run that. And what that's going to do is create that constant and assign the value to variable. Of course, if you forget to do it, TensorFlow will fail pretty easily, pretty quickly, and it's going to give you an exception saying something's uninitialized. So it shouldn't be too bad. But yeah, this is something that you typically do at the beginning of your program. And then in this case, now you evaluated it, prints the value, the 2 zeros essentially. Now let's say we create an assignment op where we want to update the values. Again, it's created this new part of the graph. It's not run it yet, so your value for v is still 0, 0. And then you actually run it, and the next thing you do, then the value at that point is 1, 2, and you print it, and that's the value you get. So you need to remember, one thing that you need to do is there's the graph creation, and then there's the running. And the reason we do it this way is having the graph be specified before running, or as much of it. You can intermix the two, of course, just like this does, right? But the more of the graph that you can define, the first time it runs the graph, first time it gets the graph, it does a bunch of optimizations, et cetera. And if you're going to run it over and over again, which is very, very common for machine learning, then it's going to be an optimized graph, except you're going to see some startup cost at the first step, but then it's going to be really fast. Go ahead.
What would it do in that fourth line if you said assign up equals v, assign v?
In this particular case, my guess is it's going to remain at 0, 0. Yeah, because it's going to evaluate the right-hand side first, get that value, and then assign it back. So yeah, I believe so. I'm pretty sure.
Hi, may I ask, is there opportunity for metaprogramming stuff? Instead of coding, why couldn't you have a graphical interface that generates the code?
I'm sorry.
Why couldn't you use the graphical interface to generate the code?
You totally could, and we haven't built one yet.
It just seems like it's a great opportunity. I mean, there is this large field to do that kind of thing, and with this kind of combinatoric and modular thing, it would be very nice to go take chunks, fill in data, duplicate it, map it across things, etc.
Right. So yeah, just for the audience, I guess. So the question was, why can't we use some visual tools to really build these graphs rather than hand coding them, et cetera? And that's totally something that's feasible. And as we build up higher level modules, so today, if you actually had to build a 10,000 node graph by visually, it's probably not going to work, right? But as we grow higher level modules that are used very commonly, it's going to get easier. And there's definitely, I know, interest by people to do things like that, and should be totally feasible. Yeah. So those are some very basic examples, right? How you might get started using variables and constants and just doing basic expressions in TensorFlow. Now let's look at some real-world examples on how you might do somewhat real examples of machine learning in TensorFlow itself. So let's take the example of logistic regression, right? Let's take a simplistic example where you have n examples of data, your inputs x, targets t, and you're trying to build a model with parameters with the weights w and biases b, and the output is the softmax y with the w x plus b, cross entropy loss to minimize that, and then you want to minimize using, say, gradient descent. Just you're doing a batch one to simplify things for now. And the idea is you want to require the gradient, you have the loss, you want to compute the gradients with respect to w and b. In this case, TensorFlow does automatic differentiation, so you don't have to worry about all of that. You just really need to build the forward pass or the loss itself. You just need to specify that. So let's look at some real code there. So in this case, we have the graph. The first thing you do is say, OK, I'm going to build this graph. In our case, we've said examples and labels are constant. Typically, you would probably read them from a file or in whatever form you have. Then you define your weights and biases as some variables, initialized to the right values, in this case, some form of random distribution. And then you define the logits and the loss on top of those. And you say, as an optimizer, I want to use the gradient descent optimizer with a learning rate of 0.5 in this case, and I want to minimize this particular loss. So once I've specified that, and here's my prediction, which is the softmax itself. So all of this step is basically built the graph in, say, 10 lines of code. And in fact, now we have more higher level abstractions that would really compress this down to even fewer lines. Basically, most of these layers can be squashed together into single simple functions. So now that you have that, for the training, you just need to add a for loop, basically, to say, OK, I want to iterate over this data many times, as many times as you like. First thing, of course, you do is initialize all the variables, then you iterate it. And as you do that, in this case, what we're doing is every 100th step, we're going to print out the value of the loss and the training accuracy by computing that. And basically, you can stop whenever you think the accuracy is good enough or the loss is good enough. Of course, this is a very simple example. In typical cases, you would probably do more things. You would handle exceptions, all kinds of things. But it's still pretty close to this. Now let's take a slightly different example of k-means clustering. So for those of you who don't know, let me just walk through quickly on what k-means is about. So let's say in this example, k is really just 3. You have a bunch of points. You want to cluster it into 3 different clusters based on how similar they are. the way you start is you start with 3 random points, or you can pick them out of the points you have themselves, and then assign these points to assign the rest of the data to each of these points, to the one that's nearest, right? So the random points that you've started out are sort of your cluster centers, and then you're saying, okay, all the green points in this case are the closest to the one cross there, the blue ones are closest to the second cross there, and the red ones are close to that. Once you do that, then you recompute the centers based on all the points that you assign to that center, and then you sort of iterate. And as you see in this particular case, so after a few iterations, you converge pretty well. So let's see how we might do something like that in TensorFlow. Keep in mind, I mean, this is not something that TensorFlow was built initially for, but because of the way we built it, it's fairly easy to map algorithms like this on top of TensorFlow. So in this particular case, we've start centroids with some random distribution. You've created as many as you want. Let's say k is the number of clusters in this case. You compute the distances using a pairwise distance function. This one's just an example. We don't really have a pdist2 implementation, although it would be very, very easy to write one in TensorFlow. And then you basically compute the pairwise distances between the centroids and the data itself. For each of the data points, you're basically going to find the nearest one, right, the nearest center. Once you do that, in this nearest case, then you basically recompute the centroids by taking the mean, the mean of your data with respect, for each of the nearest things. So basically what we talked about there. Now this builds the graph. Now we just create a session, initialize the variables, and loop through it as many times as we want until we converge, basically, right? Until we see maybe things are changing or some X number of iterations, etc. So it's fairly easy to express new algorithms that you would like in this particular way. So what we talked about so far was how do you build your models, how do you add things. But as you're training, you want to really see how things are happening, right? Whether it's really training or not. In some cases, you can just print the values just like we were doing, and that's great for debugging. But we do have some better tools, especially if you have long-running jobs or you have many of them. How do you compare them? How do you look at them? So there's this tool called TensorBoard, which allows you to really look at anything that's interesting to you in your graph. You can actually add summaries for different parts of the model, different tensors as we call them, and you can log them periodically. In fact, we have tools to help make that a lot easier. And then there's this tool on the side that charts the progress of those graphs over time. So of those values over time. In this particular case, you might say have the cross entropy value that you want to see as steps going. Is it actually decreasing or increasing, or is it bad? And in fact, if you have many runs, you can compare those. So you might try, say, 2 different learning rates, see how which one is doing versus the other, and so on. Another thing we support in there is, as the graphs become big, you want to understand what's happening there, right? This goes back to the other side of the program, just like you're saying, right? This is not really building the program graphically, but at least it's visualizing the program once you've built it in any way. So it's sort of giving you a visual output of what that program looks like. Yeah, that's basically it. And then I have some resources for you. So we have a website at tensorflow.org. And the code's available on GitHub. Feel free to check it out, try it out. There are a lot of tutorials online, so and examples too, which you can download and try it out. There are pip installs that you can do, or Docker install, Docker container that we have to make it really easy for you to try things out. Of course, if you want to change code, you can just download it and build it yourself as well. And then if you're interested in the details of our design, etc., there's a white paper as well that's linked in there that has a lot of details of the design. Cool, please.
What would you say are the closest competitors or alternatives to this?
So in the deep learning side, there are a number of other libraries that have been there for a while. I would say Theano, Torch, and Caffe are the ones that come to mind mostly. They each have their pros and cons, and they're different in some respects. Some of our ideas are from these frameworks. For example, Theano is probably the closest in some ways.
So what's the nature of the license that goes along with this?
So we've released this under the Apache license, Apache 2 license. So it's pretty open. You can pretty much use it for lots of things. Over there at the back. So the question was, does TensorFlow require that you have all the data in memory, or can you train on very large data sets? We actually train on very, very large data sets that really can't be in memory, so totally. You can, typically if you're training via stochastic gradient descent or something like that, you can really, just stream data through, reading it from wherever you want. You can read it from your local file system or a distributed file system. We support some kind of file reading, and you can really just run through that many, many times. So the question was, how big is the real TensorFlow program? Like I was saying, in our case, so our state-of-the-art image model is maybe about 40,000 nodes. Of course, that's not the number of lines of code. That's probably much smaller. I would still say it's probably a few thousand lines of code. It does build on like modules that it's built, et cetera, but it's fairly, that one's fairly complex. Some of the simpler ones, if you can use, say a sequence model where you can use a library, then you might be able to start with 20, 30 lines of code and get the basics going and then slowly add on top. Actually, there's something there.
I've heard there's a roadmap for a distributed version of TensorFlow that might use Kubernetes. Could you talk about what the plan is there?
Yes. We actually have a roadmap on the website on GitHub, so you can definitely take a look. That's something in the works. We hope to release it very soon. We're working very actively on it. We're getting close to that. So yeah, actually the question was whether we have a distributed system, and that's on the roadmap, and yes, we're going to release it pretty soon.
How flexible is it? Can you do like residual nets, batch normalization, all these new techniques that come every single day? Can you?
Yes. So the question was, how flexible is it? Can you do things like residual nets, batch normalization, all the kind of new things? So when we started TensorFlow, one of the main motivations for us was to really make something flexible that's usable by our researchers, right? And those are the same researchers that come up with these ideas. So it was very important. And yes, it supports those very, very nicely. We use it for batch normalization. We use it for trying out things like residual nets and all sorts of things. Just to repeat the question is, there are many different libraries for doing this, and going back and forth between these libraries is a headache. How do we do that? Or I guess, why do we have them, or so on? It'll be great to have one format, right? I mean, of course, everybody says yes, that it'll be great to have one format, and then we introduce one more. Totally. There are these many libraries that have been built over time. What we saw lacking there, and the reason why we still built TensorFlow, is they were built by researchers, by labs really, for continuing that research. But there was a gap in terms of, one, the kind of scaling that we need, and a lot of people need today. And two, productionization. For us, it's important to not just build these models and do research, but then deploy them as well. So keeping them separate. That's one big reason why we decided to still go ahead and do a new library. Our hope is that it's going to be, we'll see more and more people using TensorFlow and sort of picking that up and working that towards that. We see reasons to believe that, but there's we'll see what people like really. On one more side is there are people who are writing tools to do the conversions, etc. It's still a headache, but yes, it's being made easier by some of those tools.
Can you speak more to the roadmap? What are some of the things on it that might be coming out, or directions of interest?
Sure. I think a couple of things that people have expressed interest. The first one was on the roadmap was the distributed support itself, which is very important and something we're very actively working on. Another one was support for just more languages. And while we're not adding languages ourselves just yet, at least, we're trying to make it easier for other people to add languages support of all kinds. There are a few others in terms of just making it easier to do certain kinds of sparse models, and I forget what else is on the roadmap, but there are many, many things coming up. And what we would love to see is, we already see a lot of community on GitHub and people asking for things. Of course, we are very open to taking inputs from you, taking code and contributions from you. But if you have specific things that you're interested in, please let us know. Our roadmap is going to be driven by your needs, so we definitely need to know what those needs are. So the question is, can we talk about performance? How does it compare to, say, Intel MKL, et cetera? So the The broad answer, the easy answer is, I guess it depends. One thing, since we started with deep learning, our focus has been a lot more on GPUs than CPUs. So our performance in GPUs are probably much better than the CPU performance. But at the same time, CPUs are important. We care about it, especially for inference, right, in production. And we continue to improve it. In a number of cases, we know it's pretty close to the best performance. Not in every case. I mean, there are areas that we still need to improve on. So, again, if you see areas that where you need performance or you see differences, would love to hear that, would love to improve those as well. The question is, the examples that I show splits a graph among many devices, and whether it's available today or does it have to wait for the distributed version. Actually, you can use multiple GPUs on a single machine, right, even today, right? Or even with a single GPU, you might want to split between GPU and CPU, but you could have, say, 4 GPUs and split your computation across those, and that's feasible today with the code that's already out there.
But you can do computation on different nodes, for example, in the cloud.
Different machines today, no, that's not possible, but that's something that we're working actively on and should be out there soon. The question was, what kind of optimizations or how much optimization have we done in large-scale matrix multiplication, I guess. So today, what we focused on is the optimizations for, say, a single matrix multiply on one device, right? And the way you do large matrix multiplies is you can split them up yourself. Today, we don't offer libraries that do that automatically for you, although it shouldn't be hard to add those, where you can choose based on what makes sense, based on the sizes of the different matrices, if you know, where you take this really large matrix and this tiny matrix, and maybe you chop the large matrix into 4 and give that to 4 different devices, and the tiny matrix is copied to all 4, and you do the multiplication that way. So we make it very easy for you to really choose that and do that yourself. Over time, we'll add more tools so it's done automatically for you. We have very basic graph rewrites which could do those things, but right now it's still early days, and we don't have those automatically done yet. Yeah, so the question was, do we have a model zoo yet? Yes, we do, actually. We just opened it up maybe a few weeks ago. I think we've seeded it with 1 or 2 models right now. We plan to add many, many more of the things we publish, et cetera, and you'll start to see more. If you have models that you would like to put there, we would welcome that as well. So the question was, how do you see ImageNet changing now that the models are getting so big or so good at it? In fact, if you look at this year's results on the main data set, where you just look at the top 5 classification accuracy, the first and the second models were both at like 3.5 or so % error. And in fact, they were split by 1/100%. So you're right, they're getting really, really close. They're getting really, really up there. And for that particular part of ImageNet challenge, I would say, it's probably not as interesting anymore. Like there are going to be improvements, but usually not that they're not going to translate as much to the regular improvements. There are other parts of ImageNet, though. There's the localization challenge, where you also need to show, say, what part of the image is interesting, et cetera. And those are still interesting, and you'll continue to see that. We hope there'll be more data sets that people do and stuff. Google always hopes to and continues to provide new public data sets whenever it can. There are lots of efforts in that area. So, yeah.
How does this compare with things like GraphX?
Honestly, I don't know. I haven't tried to compare it. I've looked at it a long time ago, and I think there are things that can do as well that are similar. I don't think it's necessarily optimized for, say, problems like deep learning the same way. But yeah, I don't know it enough to say much more. There's some.
From the optimization point of view, there are asynchronous SGD and those kind of things. So do you guys take care of those things? Or because it's a DAG, is it mostly synchronous?
Right. So you can do that yourself. So asynchronous SGD is interesting, is mostly in distributed settings. Right. Today we don't support that, but as we do, we'll probably provide code to do that. It's not too hard to support asynchronous SGD. Basically, you need to manage independent threads and then run them independently, and you get asynchronous automatically. Synchronous stuff, you can do that, either synchronize those threads or actually add them together in a single graph as well and do both of them. So yeah, we'll definitely support both asynchronous and synchronous settings together. the question was, are there plans to support OpenCL? There is a lot of interest. I mean, if you see the issues list, there are people very interested, and we see people actively working on it externally, not as much on the team. We are supporting them. We have a developer who's working with some of them and trying to get that out. We are definitely open to it. We don't use that internally right now, so it's harder for us to add support ourselves. But again, this is an area probably where the community can help and come together to add support.
Can this be used just for a general DAG computation? I mean, do you really care that the operations in the nodes are related to ML versus I can do whatever I want, right? I mean, I have a series of data-dependent operations, and maybe you want to change the data type on the arcs, from tensors to my own thing, but
Yes.
Graphical belief net or something.
Yeah, so the question was, do you care if it's used for ML or any kind of DAG computation, really? It's really fairly general, so yes, totally, it can be used for any kind of computation, and we see some uses of that already. It's optimized for numerical computation, so as long as you're doing that, you're probably good. You can use it for anything. I mean, the data flowing through there could really be anything. We sometimes do pass different kinds
so
of
what do you map the operations in the nodes to? Threads? Are they closures all running in the same thread?
So right, so the operations are the spec, so to speak, of what you want to run, and then there are corresponding kernels that you can implement for those operations to do whatever, to actually figure out how to implement those. And you can write them in C++ using threads. We provide a thread pool that you can run those on. You provide an allocator so you can allocate things, etc.
Is it disallowed to share state in the source between the lines of code for one operation and the lines of code for another node?
So it makes sure to pass whatever data is going, like whatever is the input, it makes sure that it's available by the time in operation schedule. Yeah, sort of. I mean, not quite, but yeah. The question is TensorFlow amenable to meta models, I guess, or I guess what you mean is hyperparameter tuning in some sense, right? Totally, right? The simplest thing is, of course, you can run independent graphs, right, and figure out and manage things yourself on what the results are and what you want to run next as well. That's fairly easy to do, right? You could do something fancier where you can build some of that in TensorFlow as well using the existing operations too. And that's totally fine. Typically, people combine it nicely with Python to do whatever they want, and it works pretty well.
The related question is, can I dynamically change the graph while it's running?
Yes, although that's usually not the most optimal, right? So every time if you're running the graph for a while and then changing it, that's okay. But the first time you get a new graph or a significantly changed graph, it's going to do some optimization. So there's some cost. Although for a lot of these things, you don't really need to change graph, depending on the kind of different things you want to do, right? If it's only, let's say, changing a learning rate, then that can actually be what we call a placeholder that you can actually pass in when running the things. What I did not show in these examples is you can actually say, run this graph, give me this output, but then here's the special input for this value. So for this particular tensor, here's the value that you should use, and I pass that in. And so you don't necessarily need to change the graph to do that every time. It's sort of this value that you're passing in. So the question is, has there been a lot of use in stream processing and an integration with Apache Beam or the Dataflow stuff? Yes and no. So this by itself, I mean, in some ways, yes, you can do any kind of data processing through this, right? And people do use let's say you want to do some kind of batch predictions, right? You have a bunch of data, now you have a trained model, and you want to do predictions across the entire data set. So totally you can do either a batch thing or maybe even a streaming case as well, right? And you can do integration. We've integrated, or people at Google have integrated with some of the internal things. There's not as much integration on the open source side, but something we look forward to and hope to work with people and potentially do some of them on our own as well. I think there's. So the question is, an example of 1,000 nodes or whatever, how do you get to 1,000 nodes? Inception is maybe 50, 60 layers. Something like that, I think. So Inception is maybe 50, 60 layers the last I checked, maybe 100 layers, I forget. So somewhere in that range, right? Each of these inception layers, though, like 50 layers or whatever, is really not just one layer. It's a block of layers where you have maybe 4 parallel tracks, each of them having 3 or 4 layers. So it ends up being, if you really look at the narrow layers, then you maybe end up with a few hundred. each of those layers themselves might be made of like 4, 5, 6 nodes at the lowest level. So for example, each node is each variable. So a layer would have a weights, biases, a matrix multiply, right, with the input in addition for the bias, right? This is just for the forward pass. And a ReLU. Right. So you have 5 or 6 nodes. This is the forward pass. Once you do the backward pass as well, which is the gradient computation, that's usually more complicated. It's at least 2x that, because you have gradients with respect to the weights and with respect to the inputs. Right. So it starts to add up pretty quickly. You don't have to write that many nodes. Like the auto differentiation takes care of all of the backward pass, which is usually much bigger than the forward. But if you actually look at some of these, you look at even the simplest example that we have for MNIST, it's probably already a few hundred nodes by the time you have everything in there. But again, you don't have to add themselves manually. A lot of them are done for you. So the question was, does the CloudVision API use TensorFlow? For parts of it, it does. There are many things in there, and they've been built using different systems. But we do use TensorFlow a lot for our machine learning stuff. So wherever it's neural nets and deep learning, it's probably using TensorFlow. So the question is it useful to put TensorFlow on top of Spark and take advantage of the runtime and RDDs and so on? Yes, I would say it's definitely interesting to the people who are using Spark today. If you're using, say, MLlib for your machine learning thing, you could use TensorFlow for, say, deep learning or for some of the other things that are being added. Over time, we hope to see more integration. Again, that's, internally we have very different systems, so that integration with Spark has not been the first thing. If people are interested, we would love to see that. We would love to help you with that. Over time, we may add more things as well. So the question is, the deep reinforcement learning stuff, does that use TensorFlow? So DeepMind traditionally has used Torch. A lot of them come from NYU, and that systems come along. They do use our older system for some of the things, and there are parts of DeepMind that already use TensorFlow for certain things. They are considering expanding to TensorFlow for more and more things, but they use a combination of Torch and TensorFlow today. So the question is there a list of all the optimizations that we do on a DAG? I don't think there's a list in one place, sadly, but there are a few that I can name. I mean, for example, the common subexpression elimination we do, which is pretty handy, especially when computing the backward pass, the gradients. There's recently we've added some support for constant folding, right? If you have constants and you're just doing the same thing, we can do those. There are a couple more that we have right now, and we are hoping to add more, but I don't think there's one list right now. Are you using any? The question is, are we using any statistics for our optimizations? Today, not so much. That's something that is interesting. I know there are teams at Google that, when they know their models are certain kinds of models and they're, let's say, very sparse, they might do sparse matrix multiplies instead of regular matrix multiplies. But it's not automatic right now. We don't automatically compute stats and pick what we need to use. Again, it's something that can be added. It's we've started with this low-level library that allows you to do all of those things, and these are features that we want to add. We've talked about in some cases people are doing them, but there's a long way to go.